which is about exponential growth and decay. So we've already talked about some exponential functions in the past, especially with graphing. So now we're going to be looking at the more algebraic approach to this. So what I want you to do is to look at these three tables and determine whether these tables represent exponential growth, exponential decay, or neither. Okay, so now when you think of exponential, right, you should be thinking of rapid increase or decrease. Okay, now which causes more increase or decrease? Addition or multiplication? Multiplication does. Okay, so when we're looking at tables, if we see the numbers are increasing by larger amounts, we can create some exponential functions that involve some multiplication. So let's take a look at number 33. We see that our x is changing by 1, right? 1 unit. What is happening to my y? Well, I'm going from 50 to 10, 10 to 2, and 2 to 0.4. Well, 50 to 10 is minus 40, and 10 to 2 is minus 8. So it's not a constant change happening here. So that's going to be a hint that we have an exponential function. We don't have constant change. Well, is there anything that is constant between these values? Well, let's think about how do we get from 50 to 10 if we're not using addition or subtraction? Well, if I take 50 and I divide it by 5, I get 10. If I take 10 and divide that by 5, I get 2. And if I get 2 and divide it by 5, I get 0.4. So we have this constant division. Now, one thing you need to start understanding is that division is just multiplication by a fraction. So dividing by 5 is the same as multiplying by 1/5. Multiplying by 1/5. Multiplying by 1/5. So we would say that this is exponential decay. Why? Well, the numbers are getting smaller at a rapid pace, and more specifically, it's happening by multiplying by the value 1/5. Let's take a look at number 35. So we are going by 1, so 0 to 1, 1 to 2, 2 to 3. Okay, so we don't have to worry about how those are changing. But let's take a look at the y's. We go from 35 to 29, 29 to 23, and 23 to 17. Well, those numbers aren't rapidly increasing or decreasing. We don't start with a very big number and end with a very small number, or start with a very small number and end with a very big number. So if we actually take a look at the relationship, how you get from 35 to 29, you would actually see that if we subtracted 6, we would get from one to the other. So that's going to be not an exponential function. It's neither. In fact, when we have a constant change like that, it's a linear function or linear growth. Okay, so anytime there is a constant change of addition or subtraction, it is not exponential, it is linear. So let's take a look at 37. Are our x values changing at the same rate? Well, it's not going by 1s anymore. Now they're going by 5s. But that is still constant, so we can compare the values in our y column in the same way. How do we get from one to the other? Well, to go from 2 to 8, we multiply by 4. 8 to 32, we multiply by 4. 32 to 128, we multiply by 4. So anytime we have a constant multiplication and we see numbers starting really small and ending really big, we have what is called exponential growth. Okay? And more specifically, it's exponential growth because we're multiplying by a 4. So one key factor of exponential growth and decay is that there's multiplication by the same amount. Now, if that amount is a small number, we're going to have decay. If that amount is a bigger number, we're going to have growth. So let's look more specifically at this. So all exponential functions will be some variation of this standard form. Y equals ab to the x, where a is our initial amount and b is what we would call our growth or decay factor. Now, the great part about the initial amount, especially if there's no addition or subtraction anywhere in this equation, is that it's going to be corresponding with our y-intercept. So the a value is the initial amount and the y-intercept. B, our growth or decay factor, is the value we are constantly multiplying or constantly multiplying by a fraction by. Now, how do we know the difference between a growth and decay equation? Well, we're going to be looking specifically at our b value. If our b value is between 0 and 1, a decimal, right, a fraction that is smaller than 1, we will have exponential decay, meaning the graph will start really high and decrease rapidly until it hovers around a certain value. Exponential growth will be the opposite, okay? It'll be anything that is greater than 1. And the graph itself will start at that hovering value, and then when it gets to the bigger numbers, rapidly increase. Okay, so increasing will be growth, decreasing will be decay. Now, the one thing that has to be true, we're going to keep a greater than 0. So our initial values are going to be positive, and our b values are also going to be positive. Otherwise, we get weird multiplying by a negative, and the graph will not look nearly as nice. Okay. Now, I did say that my graphs hover around a particular value. That value is represented by the line that we call the asymptote. Okay, the asymptote is a line that a graph approaches but never meets. So if we look at these very basic exponential functions, right, our x-axis functions as an asymptote because the graphs themselves will never actually cross them. You'll never see it cross the x-axis. As long as both a and b are positive, the whole graph will be above the x-axis. Now that will change when you add and subtract values, as we talked about with graphing. But for the most part, the ones we're going to be looking at in this chapter will have an asymptote at the x-axis, which is y equal to 0. Okay, the line y equals 0. So, looking at the equations without our calculators, can we determine whether the function represents exponential growth or exponential decay? Okay, so what are we going to do? Well, we want to identify our growth or decay factor. Okay, that is the value that gets the exponent. So in this first equation, 0.65 is my initial value. And my 0.48 is my growth or decay factor. Okay, so now we look at the 0.48. What do we decide? Well, if it is in between 0 and 1, it's decay. If it is greater than 1, it is growth. 0.48 is less than 1. So that means this is decay. Okay, so if you were going to explain it, you'd say the growth factor is less than 1 but greater than 0. The second example, our initial value is 0.4. What is our growth factor? 3. Is that bigger than 1? Yes. So that means that this is exponential growth. Now, when it's in function notation, it does not change. Again, we're still looking at the base of the exponent. So 0.01, that is less than 1 but greater than 0. Decay. Now, the one thing we have to be careful of, with decimals, it's not so tricky, but with fractions, we want to make sure that we are seeing if the fraction is an improper fraction. Okay, because an improper fraction, like 5/4, actually converts to the number 1.25. So although it is a fraction, it is still greater than 1. So this would be growth. Okay, so again, we're looking at our growth factors here. We don't worry so much about the initial value to determine if something's growth or decay. So now let's take a look at some word problems. We have, each year, the local park sponsors a free throw competition. Play starts with 128 participants. During each round, half of the players are eliminated. How many players remain after 5 rounds? Well, you know this is going to be exponential growth or decay because we're in the exponential growth or decay chapter. But if this was a question that happened on a test that was mixed questions, how do you know you have exponential growth or decay? Well, it does not have a constant change, right? It's not changing by 50 every time. It's not changing by adding 10 to something. What's changing is that we are taking half of the amount. Half of 10 is different from half of 20. It's different from half of 30. So this half amount that is going to change varies every time. Okay, but still by that half amount. So that is a hint that we have exponential growth or decay. So what is my initial value? Well, we know A is my initial value. And in this question, it's 128 participants. Is it growth or decay? Well, the word half, we know half would be to divide by 2, which is the same as multiplying by 1/2. So this is a number that is less than 1. So we would say this is decay. So now what is my growth or decay factor? What will my B value be? Well, I just said it. Half corresponds to the decay factor 1/2. Okay, so how many growth or decay periods are there? Well, when does this half happen? At the end of each round. So there are 5 growth decay periods. So how do we write this as a function? Well, if we were going to write it, we'd have to fill in the values. Y equals A, B to the X. Well, Y is our final amount. A is our initial value. B is our growth factor, and X is the growth or decay periods. So we type that into our calculator, and we get that there are 4 players after 5 rounds. Okay, so that's how you would do this using math. Let's take another look. Bacteria can multiply at an alarming rate when bacteria splits into 2 new cells, thus doubling. If we start with only 1 bacteria, which can double every hour, how many bacteria will we have by the end of 1 day? Okay, well, how do we know we have exponential growth or decay? Well, it's not telling us we're adding 2 bacteria. It's saying that we are doubling. Okay, so doubling is going to be one of those key words that indicate we're using an exponential function. Now, double means to multiply by 2. Another word like this that we should be aware of is triple. That's to multiply by 3. So those are some key words that have values associated. So we're doubling, multiplying by 2. What are the values that I plug into my equation? Well, we need an initial value. Well, we're starting with only 1 bacteria. So A is equal to 1. My growth factor is what I'm multiplying by. In this case, it's 2, right? We're doubling times 2. And our exponent, right, is the number of times this doubling is going to occur. Now, we have to do a little work for this because in this question, our periods happen every hour. And we want to know how many bacteria we will have at the end of 1 day. So we need to convert 1 day into 24 hours. So my X value, we're going to substitute in 24. Okay, so when I plug that into my calculator, I get the incredibly large number 6777216. 16,777,216 bacteria. So at the beginning of the day, we had just